Three words get thrown around as if they mean the same thing, and they don't. So here's the answer up front, then we'll earn it. Artificial intelligence is the goal. The name John McCarthy picked in a 1955 proposal for a summer workshop at Dartmouth College. It covers any machine doing something we'd call thinking. Machine learning is one approach to that goal, named in 1959 by Arthur Samuel, an IBM researcher. Its trick is that you stop writing the rules. You show the machine examples, and it works the rules out. Deep learning is a slice of machine learning that does this with neural networks stacked many layers deep, and that slice took the field over after 2012. Generative AI lives inside deep learning. Large language models live inside generative AI. 5 circles, each smaller and younger than the one around it. Start with the outer circle. Artificial intelligence was never a technique. McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon built their proposal around a single sentence. Every aspect of learning, or any other feature of intelligence, can in principle be so precisely described that a machine can be made to simulate it. Notice what that leaves out. It names no method. AI is a destination, and the field has tried a lot of vehicles to reach it. For about 30 years, the vehicle was rules. Want a machine to behave like an expert? Sit with a real one, write what they know as if-then statements, and let the computer chain through them. That's an expert system, and it came out of the Stanford Heuristic Programming Project under Edward Feigenbaum in the mid-1960s. Edward Shortliff built the famous one, MYCIN, as his Stanford doctoral work in the early 1970s. Roughly 600 handwritten rules for naming the bacteria behind a severe infection and prescribing antibiotics. 8 independent specialists graded its prescriptions on 10 test cases at Stanford Medical School. MYCIN scored an acceptability rating of 65%, against 42.5 to 62.5 for 5 faculty physicians. 10 cases is not a clinical trial, but on those 10 humans scored higher. It never treated a patient, because it lived on a PDP-10 reached over the early ARPANET, and a physician would have had to type each case in by hand. Rules made real money, though. In 1980, a system called XCON went into production at Digital Equipment Corporation's plant in Salem, New Hampshire, written by John McDermott at Carnegie Mellon University to configure VAX orders so the parts a customer got would fit together. It grew to about 2,500 rules. By 1986, it had processed 80,000 orders at 95 to 98% accuracy, and DEC estimated it was saving $25 million a year. Artificial intelligence on a factory floor paying for itself. And it never learned anything. Every fact it held, a person had typed. Chess makes the same point with more glamour. IBM's Deep Blue beat Garry Kasparov in New York in May 1997, 3.5 games to 2.5, by searching 200 million positions a second and scoring them with an evaluation function split into some 8,000 parts. Its weights were fitted in advance from thousands of master games, and the Grandmaster Joel Benjamin tuned it by hand before the rematch. It learned nothing during the match, and nothing from it. Chess had been the benchmark of machine intelligence for nearly 50 years, and the machine that finally cracked it only ever improved when a human reached in and changed it. So why don't we still build this way? Because the rules ran out. Everyone had to be dug out of a human head by interview, a problem the field named the knowledge acquisition bottleneck, and the bigger a rule base grew, the harder it got to keep consistent. They were brittle, too. Feed one an input nobody anticipated, and it produced something confidently absurd rather than admitting it was lost. Worse, some knowledge can't be written down at all. Try it. Write the if-then rules that separate a photo of a cat from a photo of a dog. You do it in a tenth of a second, and you cannot say how. When the specialized hardware market collapsed in 1987, an industry worth $500 million vanished inside a single year, and the field slid into the freeze the histories call the AI winter. Machine learning answers that dead end, and the inversion at the middle of it is worth saying slowly. In ordinary programming, you supply the rules and the data, and the computer hands you answers. In machine learning, you supply the data and the answers, and the computer hands you the rules. Samuel had shown the idea in 1959 with a checkers program that got better by playing. In 1997, Tom Mitchell of Carnegie Mellon published the definition textbooks Still Lean On. A program learns from experience, with respect to some task and some measure of performance, if its performance at that task improves with that experience. Dry and exact. Here's the worked example I like. In August 2002, Paul Graham published an essay called A Plan for Spam. His filter had no idea what spam was. It counted words across 2 piles of his own email, around 4,000 messages each, and worked out for every word the probability that a message containing it was junk. Nobody told the program that the word click smells like a sales pitch. His mail told it. Graham reported missing fewer than 5 spams in 1,000, with no false positives, and handwritten spam rules were finished as an industry inside a couple of years. That's machine learning, and there's no neural network in it anywhere. Decision trees, random forests, the logistic regression a bank runs on your loan application. All machine learning, none of it deep. Deep learning is where neural networks come in, and the word deep is doing exact technical work. It counts layers. Data enters one end, gets transformed, then transformed again, and the count of those transformations is the depth. No official threshold exists, though most researchers put the line above 2. What the extra layers buy you is the thing rule writers could never get. The machine designs its own features. Early layers in a vision network settle on edges and blobs, middle layers on textures and parts, late layers on whole objects. No human picked any of that. Yann LeCun's group at AT&T Bell Labs spent from 1988 to 1998 proving it on handwriting, and it shipped. NCR put check readers into bank back offices from June 1996, and by 2001, the published estimate was 20 million checks a day, a tenth of every check written in America. Then 2012, and the floor tilted. The setup was a data set. Fei Li, then at Princeton University, had spent years paying strangers on the internet to label photographs. She showed the result, ImageNet, as a conference poster in 2009, and it grew to over 14 million hand-labeled images across more than 20,000 categories. The annual contest run on it used a trimmed slice of that. 1,000 categories, about 1.2 million training photographs. In the 2012 running, Alex Krajewski, Ilya Sutskever, and Jeffrey Hinton entered a network 8 layers deep, holding 60 million parameters, trained on 2 gaming graphics cards over 5 or 6 days. Their published top 5 error rate was 15.3%. The runner-up sat more than 10 points behind, and the previous year's winner had been around 25. That gap is the inflection point of the modern era. Within about 2 years, computer vision had abandoned hand-designed features entirely. The next hinge has an exact date on it. On June 12, 2017, 8 researchers working at Google posted a paper with the cocky title "Attention is all you need," describing an architecture they called the transformer. It let a network weigh every word in a passage against every other word at once, instead of crawling left to right. Almost everything you've used since is a descendant. OpenAI's first GPT arrived in June 2018 with 117 million parameters. GPT-3, published in May 2020, had 175 billion. On November 30, 2022, the same company wrapped a tuned version in a chat box, and 1 million people signed up within 5 days. Where does generative AI fit? It's a region of deep learning defined by what the model puts out. A classifier sorts things into bins, spam or not spam, and its output is a label. A generative model learns the shape of the data well enough to produce fresh samples from it. A sentence, a picture, a voice. Large language models are the text-shaped members of that family. Read the nesting one way, and every step holds. Every large language model is generative AI. All generative AI is deep learning. All deep learning is machine learning. All machine learning is artificial intelligence. Read it backwards, and every step is false. Which leaves the question people type next: where does data science go on the diagram? It doesn't. It isn't a ring, it's a different axis. The phrase has drifted around for decades, since Peter Nor used it in 1974, cf. Jeff Wu proposed it as a replacement name for statistics in 1985, and William Cleveland argued in 2001 for treating it as its own discipline. The job title is younger. DJ Patil and Jeff Hammerbacher coined data scientist around 2008, and Harvard Business Review published the article that made it a career in 2012. The work overlaps machine learning heavily. The goal doesn't. Machine learning aims at a model that keeps working after you walk away. Data science aims at an answer: somebody can act on this quarter. One ships software. The other ships a decision. Now the catch, which the tidy diagram hides. Those circles are a picture of what happened to work, not a law of nature. The outer one keeps moving. Pamela McCorduck called it an odd paradox, that the moment a problem is solved, it stops counting as intelligence and turns into ordinary software. Reading text off a page used to be AI. Now it's a phone feature you never think about. And the inner circles never killed the outer ones. Rule-based systems still run tax software and airline pricing, and nobody calls them AI. Some of the sharpest recent results are hybrids. DeepMind's AlphaGeometry, published in Nature on January 17, 2024, solved 25 of 30 International Mathematical Olympiad geometry problems, close to an average human gold medalist, by having a language model propose constructions to a rule-based symbolic engine whenever the logic stalled. 60-year-old symbolic reasoning, taking suggestions from a transformer. That hybrid marks where the live argument sits. One camp holds that scaling deep learning further covers the remaining distance. Another, including Gary Marcus and Henry Kotz, argues that dependable reasoning needs explicit symbols bolted back in, and calls the combination the third wave of AI. Neither side can close the case yet, and anybody who tells you it's settled is selling something. So here's the practical value of the vocabulary. It's a lie detector. Nearly every company alive claims to use AI, and on its own the word commits them to nothing, since a spreadsheet of if-then rules qualifies. Ask which circle. Is it learning from data, or following instructions a person typed? If it's learning, is it deep, and deep on whose data? Those questions have answers, and the answers separate a product from a press release. XCON stays the honest comparison. 2,500 rules, $25 million a year, and not one thing it ever worked out for itself. We didn't get smarter machines by writing better rules. We got them by giving up on writing the rules at all.